Well, good evening, everyone. I have this very fancy clock here that's keeping me honest, so we're right at 6:30 and we'd like to get started. Welcome to Living in Color, Giant Clams Up Close, a conversation with Dr. Joshua Boger, presented by the New England Aquarium Lecture Series. I'm Vicki Spruill, the president and CEO here at the aquarium, and I'm delighted to see all of you on a rainy evening, and welcome to all of you who are joining virtually. We are so delighted to be hosting Dr. Boger and grateful to the Lowell Institute for their generous support, which allows the aquarium to offer its lecture series free of charge. You all probably know that the New England Aquarium is a conservation organization that's working for a vital and vibrant ocean for generations to come. Our speaker this evening shares our passion for the ocean and is here to talk about a fantastic and fascinating marine animal, the beautiful and the gentle giant clam. Dr. Boger is the founder and former CEO of Vertex Pharmaceuticals. You may be familiar with Vertex, not only because its headquarters are here in Boston, but also because of the company's pioneering work to treat cystic fibrosis and its ongoing efforts to treat a host of other serious diseases. Dr. Boger is also an expert scuba diver with more than 800 logged dives, and he's a professional underwater photographer, which you'll see plenty of tonight. He uses macrophotography, extreme close-up shots, to explore detailed colors and patterns in unfamiliar underwater environments as a means of better understanding and appreciating ocean life. Dr. Boger holds a Bachelor of Arts in Chemistry and Philosophy from Wesleyan University and a master's and doctorate degrees in chemistry from Harvard University. Please join me in welcoming Dr. Joshua Boger for tonight's talk.
Welcome to all of you here who have braved the rain, and all of you virtually who are joining us. I'd like to introduce to you four of my friends from Fiji in the South Pacific. These are four different species of giant clams, genus Tridacna. The giant clams are the largest bivalve mollusks. They're native to the Pacific Ocean and the Indian Ocean. And they can grow, they're called giant clams because they're giant. They can grow to over 4 feet, 1.3 meters long, and weigh over 400 pounds, 250 kilograms. The clams of this size, at the large size, may be over 100 years old. So these clams live a long time. Now, many people know giant clams only from some bad Tarzan movies. It's the man-killing 500-pound giant clam who suddenly closes its massive shell and traps the leg of a hapless diver. This has never happened. In fact, the killer species in this tale is Homo sapiens. Here's a sad picture of hundreds of 30 to 50-year-old giant clam shells, likely harvested for their tough meat, only a few pounds per clam, but more so to make bird baths, lawn ornaments, and fancy sinks in hotels. This old man, old lady here, clams are hermaphroditic, so they can properly use all pronouns, is the largest giant clam that I've ever seen. It's slightly over 4 feet, 1.3 meters, weighing surely over 300 pounds, 190 kilograms, and possibly approaching 100 years old. This clam was relocated from where it was found to a marine park off the coast of Wakaya Island in Fiji. Like all clams, the giant clams are filter feeders, just like the clams you see in the supermarket. But unlike those, giant clams contain algae that live in their skin. And without the symbiotic algae that live in their skin, these giant clams couldn't get giant. So it's the way in which giant clams can grow so fast and grow so large. They both filter feed and harvest sunlight through their symbionts. Now, their algae are photosynthetic symbionts, and therefore the way they harvest light is through chlorophyll and chlorophyll-like pigments. I won't go over all the different chlorophyll pigments, but this spectrum shows that as a group, these pigments harvest light mainly in the blue and the red is where chlorophylls harvest light. By the way, that's the reason that leaves are green, is that's the light the leaves don't want. The leaves they want, the color they want, is blue and red. Now, one of my favorite giant clams is shown here. This is a rare all-blue giant clam. It's about 2 feet long, and it's situated also off Wakaya Island in Fiji, and it's not in as protected area as that old girl, and is quite shallow. From the surface, it looks just like a big blue eye. All giant clams orient themselves so that they can open up to the sun. Unlike clams that open up usually from their side, giant clams always are placed permanently, so when they open up, they're opening up to the surface. So this is a big blue eye that greets you just 30 feet or 9 meters below the surface. The key features of every giant clam can be seen on this clam. The usually more regular, rounder opening is the X-current siphon. They're filter feeders, so they pump water through themselves. The X-current siphon is the place where the water is coming out. So if you put your hand over the X-current siphon, you can feel water pumping almost continuously all the time. On the other end of the clam is the more protected in-current siphon. This is where water and suspended food, both small animals, very small microscopic animals, and other algae enter. The projections around the in-current siphon are very sensitive to touch because the clam doesn't want to accidentally ingest bigger particles, fish, and it wants to keep away from intrusive photographers. So if one of those comes up to the in-current siphon will close, protecting the clam's internal organs. Around the outside of this clam, you'll see a row of black dots. One of them is pointed to there. Those are actually eyes. They're actually pupilled eyes. There are holes in the clam, and at the bottom of the pit, there are around 100 light-sensitive cells. So it is a focal pupil with a primitive retina on the bottom. And except for with our pathetic 2 eyes, this clam has hundreds and hundreds of eyes. Now we know that they actually are used to focus because you can move your hand close to a giant clam, a foot or 2 or 3 feet away, so that you're not casting a shadow on the clam. You're just within the visual field of those eyes, and the mantle, the skin of the giant clam, in that area will retract. If you do it a lot, the whole mantle will retract. So they communicate with each other, but they're sensitive to just something approaching the giant clam. They also keep track of how much light generally there is in the neighborhood to see if the clam might want to close for the night. That deep color is startling from 9 meters, but it's even more startling up close. This is a close-up look at the mantle, the skin of this quite rare all blue giant clam. You can see there's really a continuous blue interrupted with patches of gray or almost black. More typically, other giant clams have multiple colors. This looks like an eye of some creature, but it's actually the almost perfectly round X-current siphon of this giant clam spouting its water. And you see all around that irregular patterns of gold, yellow, and blue against a brown background. Up even closer, I imagine that this texture looks more like a hypothetical blue-spotted giraffe. Now, it's not all brown, yellow, and blue. This beauty has blobs of green rimmed with yellow on a dark background. Notice also in this close-up, this is a close-up on a partially closed giant clam. Its shell is at the top. The shells wave like this. The shell is at the top and the shell is at the bottom, and it's partially closed. And notice those closures don't quite meet, which is very common for a giant clam. A giant clam couldn't catch your feet even if it tried, because it doesn't close its shell completely. Often close-ups of giant clam mantles remind me of something else. This looks like nothing more than a fantastic cloth that you would love to make something out of. My imagination sometimes runs a little bit wilder than that. When I first saw this clam seen with its in-current siphon closed, that's right at the top middle of the picture, and its excurrent siphon opened, and on either side is the mantle of the clam. I call this shot Green Lady Cyclops. This view of one side of a brown clam and gold clam I named Lady Reclining. And this excurrent siphon picture just called out to be named The Scream. This looks like a gold-rimmed eye or a Japanese abstract watercolor, and of course it's the giant clam excurrent siphon. So we have all this color and diversity, and it raises some interesting questions. The chief of which is, what's up with clam colors? Clams are colored, but they're not colored for reasons that most animals use color. They're not using it for camouflage. That blue clam is hardly not standing out. They're not used for signaling. They are immobile for 100 years. The clams aren't looking for mates. They are hermaphroditic. They put out eggs and sperm periodically into the water. They cannot fertilize themselves, so they're just looking for those eggs and sperm to find a pair. They don't go on dates, so they don't need to look nice. Maybe a clue to the colors would be to ask another question, related question: how does the clam form its color? How does the clam use color? Does the clam tune colors, or does it just take the colors it has? And how does a clam choose to have the various patterns? You've seen all kinds of different choices made by closely related species. Now, before I answer this question, or these questions, I have to give you a little information about how color is treated in water, particularly in the ocean in these cases. Water absorbs certain wavelengths of light. As you go deeper in the ocean, water absorbs increasingly large amounts of red, some orange, a little bit of yellow. Blue light makes it all the way down to 120 feet, almost unimpeded. If I were to dive 120 feet in the Pacific, in the clear water of the South Pacific, it's as bright as your living room. You don't see any darkness down there, and your eye cannot tell that there's no red light. You don't have a spectrophotometer in your eye. So even though there is zero red light at 120 feet, you say it's still bright down there. So when you look at something down even 30 feet, this is a picture of a beautiful a red and white soft coral in Fiji, down about 30 feet, around 10 meters. And with a flash, it's white and red. That same picture taken without the flash looks like this. So this is what your eye sees without a flash. And the question of what is the real color is an existential one that I leave as an exercise to the audience. But I think it's red. It's a red and white soft coral that happens to have no red light where it lives. So think about that as we ask the question, where are these colors coming from? The answer is it depends on the color. If you look at this clam and focus on the brown area here, you can see in this picture what looks like some splotchy dots in that area. If you look at that microscopically, what you'll see is that those are small groups of algae that are embedded very shallowly in the skin of the giant clam. So they are down no more than 0.5 millimeters, 2/100ths of an inch into the skin, but they're right under the skin. And they're brown because that is the color of these algae. If we go to another area that's more colored and look at, let's say, the green dots there, there's a more amazing thing happening. So I'm going to take you to a diagram of what's happening underneath the green areas in that circle. In the green areas, the algae are displayed in a different way. The algae are in what called pillars. They are long tubes of algae that go down very deep into the mantle, 10 times deeper than they were in the brown section of clam. And on top of that, there's some clam cells called iridocytes. Green, because we picked out the green area to look at. And it's somehow this arrangement that's causing a different arrangement of the algae, and something is causing the green color. But it's not the iridocytes, because the iridocytes contain no pigment. There's no pigment in the giant clam that's green. So what's happening here? The solution to this mystery, which was a mystery for many years, was proposed only in 2014 in a paper by marine biologist and biophysicist from Duke, from University of California, Santa Barbara, from UPenn, and even from NASA. And they pointed to the fact that these iridocytes look very much like diffraction grids. Color in diffraction is common on land, most common seen in things like a butterfly. The butterfly wing is blue because it has chitin layers closely spaced that diffract the light. Light coming in is diffracted so that certain colors are bounced back and other colors are absorbed or go through the chitin. So the butterfly is using its dead skin to change what light bounces back. It doesn't have any blue pigment in the butterfly wing. So that's what's happening with iridocytes as well. These closely spaced layers, though, are not dead skin. They are live membranes in living cells called iridocytes. And unlike the butterfly, the goal is not to refract certain light back because the clam wants that light reflected back, but to drive selected other colors downward. And the colors that it reflects downward most strongly are, if you've been paying attention, blue and red, the colors that algae eat. So the iridocytes are selecting the light out of the spectrum that the algae most wants and sending it downward. And it's sending it downward in a dramatic fashion. If we take direct measurements of different light colors onto clam mantle skin and measure their penetration into the skin, what you see is that where there are no iridocytes, blue and red light hardly penetrate the skin. The axis at the top is percent of the radiance is transmitted, and it's on a log scale. So down at 1, you're down at 1% of the light getting through. And you can see that even in a few hundred microns, a few tenths of a millimeter, there's essentially no red and no yellow light gets down in the skin. That's why in the brown areas, the algae is concentrated very shallowly in the skin. But with iridocytes doing their pumping of light down by diffraction, you get 5 to 10% of the light going down 30 times deeper in the skin. So the clam is created a biophysics way to pump light down and arranged a home for the algae in a pillar so that that pumped light is driven down to the sides of that pillar deeper and deeper and deeper into the clam skin. A biophysics model agrees with this pretty well, showing that this theory is undoubtedly accounts for most of the activity here. This is a biophysics model of clam skin showing that almost no blue light gets down into the skin. That's the purple curve. And if we just put the pillars there, just align the algae in pillars in tubes like that, you get a little bit of an improvement, but you only get about 1% of the light getting down in the skin. And only with the iridocytes that are arranged in as a grid do you get as much as 10% of the light down in deep in the clam. So the bright colors seen in giant clams is from diffraction, but it's the backscatter we see, not the color the clam is creating. So it's the opposite of the butterfly wing. The important color is the color the clam is the least important color is the clam showing to you. Now, this accounts for that clams are colored, but it doesn't actually completely with the efficiency of giant clams. There's something else going on. And in 2020, there was a paper that addressed these following two questions. Do clams tune the light? We saw them selecting light, but do they actually tune the light? And more importantly, how does the clam choose its colors? And this has to do, again, with iridocytes. This paper appeared in a Saudi Arabian group that looked at iridocytes and looked at them more closely. These are our familiar iridocytes. Those are the grids in the left-hand close-up of the grid, the gridded membranes. But they did a chemical analysis of these iridocyte grids, and what they found was that there was crystallized guanine plates on these grids. Now, guanine, if you remember your high school biology, is important in DNA, but here it's being used for a biophysics purpose as a chemical, as a photonic chemical. What we see if we measure more carefully the wavelengths of light transmitted through a giant clam skin is that with iridocytes that have this guanine plates, high energy light would be 325, ultraviolet light in purple, is actually shifted by photoluminescence to blue and red. So if you shine ultraviolet light on the iridocytes because of the guanine, it changes the light to blue and red light. Pretty magical. If you shine blue light on the clam iridocytes, it changes almost all of that blue light to red light. And if you shine red light on the clam, it keeps it like it is. So high energy light is shifted to lower wavelengths by these guanine crystals in these iridocytes. This, if you just take guanine powder, this is a property of guanine. If you take guanine powder, you get essentially the same directionality of shift, but it's much more dramatic by putting it into crystals and putting it into this grid. So looking at our different clam colors now, in the brown giant clam area, and the areas of brown in a giant clam, there are high levels of algae, but they're mostly shallow. This is a cut through of a section of giant clam skin, and you see that the highest levels of algae are the shallower ones, and it gets less and less as you go deeper into the skin. This is what we would expect. In the blue area of a giant clam, which has the iridocytes, what you see is that there's algae all the way down, and indeed the algae gets more dense the lower you go. And that's, again, what you would expect because the iridocytes are pumping light deep into the clam skin. So you have, in the brown area, you have low iridocyte levels, more symbiont chlorophyll There's quite a lot of algae in the skin, but it's all shallow, and you get a red fluorescence from chlorophyll that gives the red color to the brown clam. In the blue areas of giant clam, where the high iridocyte levels and high guanine levels, there's less symbiote chlorophyll shallow, but maybe as much all the way down or more all the way down and deep in the clam. But what you're also getting is protection from high energy light. Clams get sunburn. Algae gets sunburn. In fact, one of the predominant causes of algae bleaching on coral can actually be sunburn. Too much light causes algae to reproduce too fast, producing toxic waste. And in the case of clams, this can kill the clam or kill the algae. So keeping too much light away from the algae is a service to the algae in a high light area, particularly a shallow area. Remember our blue clam? I said it was unusual and it was unusually shallow. That clam is so shallow, its main problem is that it gets too much light. And so to keep its algae alive and happy, it's covering all of the surface with iridocytes, reflecting back that damaging blue light and taking the blue light and the violet light and the ultraviolet light and shifting it to red. Deeper down in the iridocytes with the guanine are creating red light that would never be there. You have chlorophyll and algae that love to eat red light. Down below 30 feet, there isn't any red light, but there's blue light. And so what the clam does is with the iridocytes and the guanine is shift the blue light to red, feeding its algae with red light. So there's quite a lot of magic going on there. So why aren't they one color or the other, just like that blue clam? It's because conditions in the ocean and conditions in the weather and conditions in the climate are not the same every day. And so the clams that are multicolored are likely making a statement to optimize the good of the whole community. As maybe a metaphor for our times, it may be the best thing for algae on one day to be below an iridocyte or not below an iridocyte. But over a period of weeks and months, it's better if some are in one place and some are in the other place. The diversity of color is an advantage to the clam, if not on any day to the individual algae. The clam is playing the odds by being colorful, and it's providing something for every lighting condition. So what do we learn in just a few minutes about clams and color? Giant clams create biophotonic diffraction arrays to drive selected wavelengths of light deep within their skin. The color you see is a byproduct of feeding light to embedded symbiont algae, and the color you see is mostly the light they throw away. Giant clams convert some damaging high-energy light to longer, safer wavelengths, precisely the wavelengths the algae is wanting. And they generate different colors by varying backscatter and balances of clam guanine crystals and algae chlorophylls. The different colors, therefore, are a design response to light conditions in their permanent home. These clams have created the optimal home for the algae on which they depend. Now, I'll close with just this editorial comment. We're not likely to save giant clams for what they teach us about biophysics. So let's all appreciate and honor giant clams and coral reefs and marine mammals and our delicate ecology of the ocean for its intrinsic worth and beauty. It's our only planet. Thanks very much. I think I'm on.
Good evening, everyone. My name is John Mandelman. I'm the Vice President and Chief Scientist here at the New England Aquarium, in charge of our Anderson Cabot Center for Ocean Life, which houses our ocean research, policy, and corporate and industry advising work. It's my pleasure to be here and have a chance to chat with Dr. Boger after an amazing presentation. Love that. Phenomenal, and things you've seen underwater, mind-boggling. So I'd love to start with a question, and then I'm going to invite the audience to ask questions, and I will repeat your questions. I'll also intermittently take some questions from the virtual audience. Welcome to those tuning in remotely tonight for this wonderful lecture. So my first question is actually, I'll credit it to Vicki Spruill, our CEO, who introduced the lecture and had to depart. She asked Dr. Boger if your work, or not your work, but you're seeing clams in the wild and your fascination with these different species, has that in any way influenced your own professional work, your vision for biomedical research, Vertex and beyond?
Well, I've long had an appreciation for what the world can teach us. I mean, an example here is this amazing biophysics of the clams. It must occur to people that, gee whiz, this might be useful for other things. These clams have been working out how to capture light for 100 million years. And whenever I encounter anything in the living world in particular, I see this lesson over and over again. The lesson over and over again is that the amazing problem-solving ability of evolution is awesome. And so I'm fascinated by that, and that causes me to say two things about biomedical research. One of them is that given enough time, you can solve any problem. Evolution teaches us that as long as you're flexible. So I study the way, particularly the way natural environment is built as a system to stay flexible. Because that's the way the body's put together. So all of this together in my education, in my mind, is all of a piece, and it's an appreciation for the amazement of life.
Thank you. Question from the audience. Right here in the front row. Hey, John.
Thank you, Dr. Mantlin. It's really striking that you have such a convergence of function to kind of modify the wavelengths of light to facilitate having symbiodinium between these guys and corals. I'm curious if you're aware of any other mechanisms that the corals have for hosting a symbiodinium that they're not exactly conserved, but at least similar between giant clams and a coral.
Repeat that question in its simple form.
Yes. So the clams and corals are both modifying the color of the light to make it easier to have symbiodinium that feed them. Do the clams do anything else that people are aware corals do to host symbiodinium?
The question is, do the clams do anything else similar to corals to host their symbionts?
Yes.
So the answer, of course, is the shell. So as you know, one of the nighttime terrors of algae in coral is that some fish is going to come and crunch a piece of the coral out to get to the algae. So by the way, that's how you get the sand on your beaches. But so it has some benefit for us, I guess. But for the algae, it's not a good thing to be eaten by coral. And the clam has another solution for that, which is if such a creature came to the clam, it just closes up, and no fish is going to get through that clam shell. So it's a unique protection mechanism for the algae. I think that's the one that occurred to me the first.
Thanks. So a question from the online audience, sort of a chicken or the egg question, Dr. Boger. Did you know about giant clams and get interested in them before you started diving? Or was your diving in Fiji and other places what inspired you to fall in love with these species?
So that's clear. I had the same vision of a giant clam as the Tarzan movie before I saw my first giant clam. And so it was seeing these magnificent creatures and appreciating them first for who they are and what they are, and then, because I can't help it, asking the scientific questions around them. But I try not to let the science get in the way of the beauty. To me, the science only enhances the beauty. When I look at the clam in front of you right now, I think it's more beautiful because of because the diversity of color has such a magnificent function. I think that adds to the beauty.
That's a great way to put it. Question from the audience. Way in the back, is that Ashley?
Yeah, that's me.
Hi, Ashley.
Hey.
Okay.
So a lot of the work being done in your studies show that the conditions in which these clams live in and the varying depths of that algae show that different color. So normally the life of a giant clam is very stationary and in one spot. But have there been any studies or have there been any cases in which a clam moves, let's say to like an aquarium, and there is some where the clam is able to change color because of those change in conditions?
So the question is, interesting question. The question is that these clams are stationary. Have there been any cases where they've been transplanted or moved, say, to an aquarium and change color?
So that's a great question. And with something that lives 100 years, it might take a while to get the answer. It might not happen overnight. But I do know that oldest giant clam that I put the picture of was moved from a deeper place to a shallower place. It's only been there about 4 years. I haven't seen, in the time that I looked at it, which was over a period of about 2 years, I didn't see any difference in its color. But that may not be enough time for it to adjust. I know, as you know, the symbionts in coral can change rapidly in response to conditions, and that's been documented with temporary ocean temperature rises that have caused the clam to bleach and repopulate with another species. That other species, by the way, in the case that I know about in coral, was present in the environment. It just was a minority species, and it sort of took over because it had more temperature. It had more temperature tolerance. But then when the temperature went down, it got kicked out, and it repopulated with its normal algae. I don't know any study like that for clams, but I also know that I don't know more than I know.
Excellent. So we'll take an online question. Interesting one. Do clams, Dr. Boger, have an immune system? Or do these giant clams specifically?
They have a nervous system, and they have a nervous plexus, and I do not know the answer to what they have. They have an immune system. They do shuttle food and nutrients to the algae. So they have channels where they get, they're feeding the algae with phosphate, nitrate, and carbon dioxide. So there's a circulatory function, but I'm not aware of an immune system that I've read about. It's a good question.
It's a good question. The audience, yes, yep. I didn't catch the end, but the question was, do you see a color differentiation as a function of age in the clam? Is that correct?
Yes.
Okay.
Not by my observation. I see a clam that's as beautiful as this. I've seen them as small as 2 or 3 inches long, which would be very young. They grow very fast, these giant clams. They grow very fast, up past 6 inches pretty quickly. You don't want to put one of these guys in your aquarium unless you're prepared to have the glass broken. But they grow very fast. But even small ones, I've seen small ones with very intricate patterns of color. Again, why a particular small one chooses to be a particular color or not, a particular pattern, no two clams are alike. They're like fingerprints. So these are not exact patterns because of species, but they do have inherited propensities to be certain colors. But I wish I knew that. I wish I knew the history of that large blue clam. I have a feeling that that clam did not get that large sitting where I see it. It's almost too large to be as shallow as it is because it would get too much damage. The other than man, the real killer of giant clams is sand. So if a storm comes up and the clam doesn't close up completely and gets covered with sand, it's kind of the end of the road for the clam because it can't move. This blue clam is just sitting there in the wave zone or close to the wave zone. So I have a feeling it was transplanted there, and the blue must have been an adaptation to being shallow. Another question. That's a hypothesis. I didn't observe that, but that is such a rare color to be in a large clam that it must have some rare history.
So that leads actually to an interesting question from our online audience about depth preference and what determines the strata that these clams settle in.
Well, the clams are rarely seen below 80 or 90 feet, but I've seen them down that low. Of course, the ocean depth varies with time as well. So even in 100 years, it can vary with some land changes. In Fiji, it's volcanic. It's not active, but there are subsidence changes in Fiji. But I rarely see them. I've rarely seen a clam lower than about 30 meters, and that's because it's just hard to get light down there. Blue light gets down, and you would think you would be able to get the transmission of blue back to using blue and red enough, but I think that may be a selection process that the young clams don't get through. Being a young clam is a tough business. They mostly don't grow up, and so the ones you see are the ones that have chosen particularly good places to latch on. They latch on permanently very, very early. They latch on early in a few weeks, and they may maintain their ability to move a little bit for a few more weeks, and then they're done for 100 years.
Fascinating. Question from the audience.
I had a question about the shape of the shell.
Yep.
You showed a picture earlier, and you said that the shells don't always close. I was wondering if there's an evolutionary advantage to having that ridged shape rather than just closing like a muscle or something else. Because it doesn't seem like they have predators to pull them open or anything like that. So I was wondering if you could do that.
So the question is there an evolutionary factor involved in the shape, the ridges of the shell in these giant clams?
Do not know the answer to that. I can tell you a little bit about the shape, though. The true giant clam, which is Tridacna gigas, which is really the only clam that should be called giant clam. It's the biggest of the species, and that was a gigas that I showed you, the largest one. Has 4 or 5 ridges on either side. So it's very big, but has relatively few ridges on either side. The more common species have 6 or 7 ridges on each side. I can only speculate that as these clams are opened up, they splay their mantle over the ridge, and so if it's variegated like that, there's more area, there's more surface area for it to splay its mantle, and it can push its mantle out quite far over the edge, and if it's very relaxed, it will be quite a bit over the edge. As an intrusive photographer comes near it, it sees me and pulls in, but doesn't close. It just pulls in the mantle. But on a nice sunny day, it's out there on the beach. Taking as much sun as it possibly can. So that's a speculation that it's a surface area maximization thing.
Makes sense. Another question from the audience. George.
Since most of these are threatened or endangered through most of their range, what role do you see aquaculture for both food and the aquarium trade is having on these?
So what role would aquaculture have on these giant clams, if any?
Well, aquaculture done properly I think could be quite useful in the sense of if you culture giant clams and eat 3 and put 1 in a protected area, I guess that's a good deal for clamhood. That aquaculture is very avidly done in Fiji. The government supports it. There's at least one there's one island that does that's their industry, supported by the government, and they raise clams up to a foot and a half, and then they look for homes for them. And the government has a program that says that either private islands or towns and villages on publicly owned islands can get tax breaks if they will take a special marine preservation area for these giant clams. And so they take these orphan giant clams and put them in for a tax break. I think that's been pretty successful in Fiji. The math of whether it's going to save the species or not is not good. When you take a giant clam out of the wild, you're doing enormous damage to the population because of the way they breed. As they say, they're hermaphroditic. They put out 500 million sperm and eggs at various times. By the way, interestingly, they time it all and sync with neighboring clams, even though they don't talk. They use chemicals to do that. But they put these out in the water. If you take half of the giant clams in an area out of the ocean, you decrease their fitness by a factor of 8. So you don't have to take many clams out to decrease the natural fitness of a clam population. So if aquaculture that diverts at least some of the raised clams to the natural environment could be a way to mitigate that. It's not going to save the clams in Philippines, though. The clams are almost gone from the Philippines.
Another question from the audience. Yeah, you had your hand up for a while.
Yep. Anyways, so my question more is kind of tying back to the whole symbiotidium thing. I know that they have it, that they're very similar to coral in a lot of aspects. Do they bleach like coral? Are they able to recover like coral? Like how do they impact with what's going on with climate change?
Interesting question. So the question from the audience was, are they similar to coral in as far as the symbionts are concerned? Do they suffer bleaching and can they recover from such? And how does that interface with climate change?
Someone in this audience must know the answer to that question. I have never heard of a giant clam bleaching, and I've certainly never seen one, and I've seen giant clams in areas where there's coral bleaching. So they must be protecting their symbionts against that bleaching in ways that coral hasn't figured out, because I've never seen a giant clam, even a patch of bleaching. I've never seen it, and I've been in areas where there's been substantial bleaching of the coral. So, since as you said, they are often the same species of symbiont and are, in any case, very closely related, it's not explained by a species difference, I think. So that's an interesting thing to follow up. How is the clam protecting this? I can only speculate things. One of them is that, remember, the clam is a filter feeder. It's actually cleaning the water around it in the neighborhood. What?
Corals do similar things.
Yeah, but not as these clams are pumping lots of water.
Yeah. So.
Do you know if it's the same species?
That's been documented. There are as genetically identified. There's some of the species crossover. Yeah.
So notice to the symbionts, hang out with the clams, not the coral.
Clams.
Got it.
Clams are a better condo.
Yeah. Sounds good.
Yeah.
All right. A quick question from the audience before we jump to another one, or from the online audience before we jump to another one here. Seasonal layering of shells. Does that occur? Do they lay down or deposit shell as they grow in a seasonal way, or is there any kind of a pattern? Maybe that links to aging. in some way?
I've seen the cross-section of a cross-section cut through. You see them unfortunately, I've seen them in sinks in hotels.
Yeah.
And I don't see any layering in that. I don't think it's a seasonal thing. Remember, these clams are at least the ones I've seen, are most prevalent in very close to the equator in the South Pacific, and there are in the Indian Ocean. I haven't seen them I haven't been diving in the Indian Ocean, but it could be, seasons aren't such a big thing in Fiji. Summer is 12 and a half hours of daylight, and winter's 11 and a half hours of daylight.
Right. Yeah, right there in the middle.
I'm just curious if there are any other kind of marine life besides corals that use light in the way that the clam does, or depend on light in the way these species seem to.
So the question is, are there other critters in the ocean or species in the ocean that rely on light other than clams and these clams and corals?
Well, I mean, the answer to that is surely yes. I mean, there's plants in the ocean of all kinds, not as obvious as the plants on land, but there's not only plants in the water. The algae there's a lot of algae in the water, and they depend on light. But there are also plants. There are algae that are independently growing algae and other plant life in the ocean. I'm thinking of other animals, and I don't know I think the color in the animals that I know about is more typically there for the reasons why animals have color, and I don't know of any other animal that gets its color the way clams do and uses light the way clams do. I've asked this question in a couple of audiences, and I hope someone is going to pop up and give me the answer. I don't know of another example of diffraction in the animal kingdom with a live membrane. So someone's going to tell me that answer, but I think it's the only example that I know of where diffraction uses a live energetically maintained membranes for diffraction.
Online audience, anybody know the answer?
Know the answer to that.
Do you have the answer, or do you have a question?
I have a question.
Okay, we'll take a question.
So is this mechanism unique to giant clams, or are there other species, genus of sort of smaller, more regular clams that use something similar?
So the question is this mechanism unique to larger species of clam, or do the smaller ones exercise or use a similar mechanism?
Don't know the answer to that question. I do know that the growth rate of giant clams is notably higher than the growth rate of most other clam species that I know about. So these guys may not need this symbiotic algae in their younger years, even though they have it. They absolutely require it in even their teenagers' years, because they just couldn't grow as big. I don't know of any other clams that have that constraint.
Online question: predation other than humans. Anything else? Dig eating the mantle?
Yeah, there are a few fish that occasionally go in and take chomps out of the clam. The clam usually recovers from those, so it must have some kind of immune system. Back to the question, if you count that an immune system, it can recover from wounds. So that if you count that an immune system, the answer is yes. So it can have chunks taken out of it. I've never seen one, so I don't think it happens very often. I don't think there are too many fish that want to go in and do that. They're certainly not swarming around giant clams routinely. It's mainly people. I think there's some starfish that may occasionally go after some of the smaller ones. The smaller ones, everything I'm saying about giant clams is about the larger ones. Baby giant clams have a tough life, so they may have all kinds of predation going on. But the big guys it's just us.
Any other questions out there? Yes?
What are conservationists doing to save the giant clam?
So the question is, what are conservationists doing to save the giant clam?
it's a tough one. There's the horrible cultural falsehood that the adductor muscle of a giant clam is an aphrodisiac. That's a death knell for any animal. You got to tell people that's stupid. And I cannot imagine that it's a great eating experience. It's one of those I ate a giant clam bucket list things, I guess, for some people. And then you've got to actually shame people against the use of the shells. That's what I try to do. The way conservationists are approaching this that I know of is by culturing and placing orphan clams in the environment, because you can really make up for a lot of predation if it's not gone too far just by increasing the population in local areas of ocean. But we got to stop thinking that bird baths are worth killing a 100-year-old clam over.
Amen.
The birds don't care.
Yes, the green scarf.
Thank you. I'm a human development person, so I would like to know at what age you got in the water and saw something fascinating, and at what age, when did you get to Fiji, at what age, and where did you grow up?
So the questions are, where did Dr. Boger grow up? When did he get in the water? Scuba diving, and Fiji for the first time.
So I grew up in North Carolina. I don't ever remember a time I couldn't swim and swam in the ocean, I'm sure, over my head at 3 or 4. I didn't start scuba diving until I was in my middle 40s. So I didn't go down. And I hate snorkeling. Snorkeling is way too much work. You have to suck air down against a pressure differential, and I just don't like to suck air. So until I found out that scuba diving doesn't suck, then I didn't think of it. But when I had children going to the age where they could scuba dive, I thought it would be a neat activity. So I became certified ahead of them, so Dad would have a skill that they didn't have. That approval lasted for a few years. But I became hooked by it. But I've always liked the ocean, and the ocean is my friend. When I go out in the ocean, and this is true since certainly as I was a teenager, I would swim out in North Carolina, South Carolina beaches. I would swim out and stay 4 hours out offshore on the past the wave line, and just swim back and forth and float in the ocean. So that's me at 15.
Thank you, Dr. Boger. So one of our online audience members points out, according to PubMed, that bivalves in general do have immune responses to infectious diseases.
Good.
There you go.
Good.
So thank you, and thank you to the audience as well. Great questions. Online audience as well. Thank you for helping educate us around giant clams. Tonight's event was made possible, again, as Vicki noted earlier, with the generous support from the Lowell Institute, who allows the aquarium to offer these amazing lectures and learn these amazing things about these amazing creatures for free each season. If you enjoyed this program and want to help support our ocean conservation and education work at the aquarium, please consider giving to the aquarium's Mission Forward Fund at neaq.org. If you're with us in person this evening, we have a cash bar in the lobby. It'll be open for another half an hour subsequent to departing the auditorium. Please join us. For those of you that joined us virtually, thank you so much. Again, fantastic questions. Love that people tune in remotely. And yeah, come back to our next lecture. Do we have I don't have information on our next lecture. TBD on the next lecture. Stay tuned. Great to have you all tonight. Thanks for braving the weather. Thanks for hanging out with us. Thanks for spending time with Dr. Boger.